Objective, simplifying radicals. Definition number 1, a radical sign. This symbol right here indicates a principal or non-negative root of an expression. Remember, the principal root, the principal square root, is not negative. Definition number 2, a radicand. This is the expression underneath the radical sign. So whatever you see under this mark is the radicand. Definition number 3, radical expression. It means the expression contains a radical sign. Here you have a radical sign. The piece underneath is called the radicand. This little number 2 is an exponent, and the index, if you don't see it, it is 2. It's invisible, so that means it's a square root. It could be another number, maybe it's 3. Now it's a cube root. It could be a 5, and that would mean the 5th root. It can be any number called the index. A radical is in simplest form if no radicands have a perfect square factor greater than 1. It's also in simplest form if no radicands contain fractions and no radicands appear in the denominator, so the bottom of a fraction. No radicals in the bottom of a fraction. The product property of square roots. For any number a and b, where a and b are both greater than or equal to 0, we have the square root of ab, so this is the square root of a times b, as our radicand. We can separate it into 2 square roots, the square root of a times the square root of b. Big number 1, there are 3 parts. To simplify a square root, first, determine the largest perfect square that will divide evenly into the radicand. Then, write the radicand as a product of the perfect square and another factor. Part C, take the square root of the perfect square and write it on the outside of the radical. Leave the remaining factor underneath. So the square root comes out, the other factor stays inside. Here are some examples. Example number 1, the square root of 147. So you have memorized the list of the first 15 perfect squares, and now you're going to pick the biggest perfect square, the largest perfect square that goes in evenly into 147. And this is going to be 49. From our list, 49 is a perfect square. 49 goes into 147 3 times. So I can rewrite, instead of saying 147, I can say 3 times 49. Now, the next step says take the square root of the perfect square. Well, 49 was the number that was a perfect square, and the square root of 49 is 7. This number comes outside. The 3 stays inside the radical, stays underneath as the radicand. Example number 2, the square root of 605. The biggest perfect square that goes in evenly into 605 is 121. 121 goes into 605 5 times. So I can rewrite 605 as the product of 121 times 5. The square root of the perfect square, the square root of 121 is 11. This number comes outside the radical. 5 stays inside. Example number 3, the square root of 72. Think to the list of perfect squares. The biggest perfect square that goes into 72 is 36. 36 times 2. The square root of 36 is 6. The 2 stays underneath. Now, you might have been thinking that 8 times 9 gives you 72, and 9 is a perfect square. However, that 9 is not the biggest perfect square that goes in evenly into 72. 36 is. So 6 times the square root of 2 would be your answer. Example number 4. The square root of 5 times the square root of 35. So I have two radicals multiplied by each other. I can break down the square root of 35 into these two products, the square root of 5 times the square root of 7, because 5 times 7 is 35. Now, using the product property, I can rearrange these in any order. I can say 5 times 5, which gives me 25. So the square root of 5 times the square root of 5 is 25. And here I just bring down the 7. The square root of 25 is 5. So the radical disappears. This is equivalent to 5 times the square root of 7. Example number 5. So this one's done a little bit differently. Instead of breaking these into products, I multiplied these two together. So the square root of 6 times the square root of 10 is the square root of 60. Well, now I'm looking for the biggest perfect square that goes into 60, and that is 4. 4 times 15 is 60. So now I'm going to do like I did in these three examples. The square root of 4 is 2, and 15 stays inside. There isn't a perfect square that goes into 15. Division property of square roots. For every number a and b, where a and b are greater than or equal to 0, b is greater than 0, can't be equal to because it's in the bottom of a fraction. We can't have 0 in the bottom. The square root of the fraction a over b is equal to the square root of a over the square root of b. So I can say this is true because I can break the fraction into two pieces. The whole fraction is underneath the radical, so I can say the top is underneath the radical and the bottom is underneath the radical. Using this property, example number 6, the square root of the fraction 11 over 49. So I can separate it into two pieces, the square root of 11 over the square root of 49. Well, the square root of 11 isn't a perfect square, so I can leave it in this radical form. However, the square root of 49 is 7. And this is in simplest form. I can have a fraction, I just can't have a radical in the denominator. Example number 7. The square root of the fraction 25 over 4. So let's separate this into two pieces. The square root of 25 over the square root of 4. The square root of 25 is 5. And the square root of 4 is 2. So I'm going to leave my answer as 5 over 2. Alright, simplify by dividing first. Example number 8. The square root of the fraction 88 over 11. Well, if I broke this into two pieces, the square root of 88 over the square root of 11, I wouldn't get anywhere. It wouldn't be any more simpler because 88 and 11 are not perfect squares. So, if I divide the fraction first or reduce the fraction, then I will be able to simplify the radicals. So, 88 divided by 11 is 8. The square root of 8. So now I'm looking at the list of perfect squares and I want to know the biggest perfect square that goes in evenly into 8. And that's 4. 4 times 2 is 8. 4 is the perfect square. The square root of 4 is 2. This square root of 4 becomes this 2. However, the other 2 stays inside. Example number 9. The square root of the fraction 12 over 27. 12 over 27 can be reduced. 12 and 27 are both divisible by 3. 12 divided by 3 is 4, and 27 divided by 3 is 9. Now these are two perfect squares. So I can rewrite it as the square root of 4 over the square root of 9. The square root of 4 is 2. The square root of 9 is 3. So now I have no radicals, and I just have the fraction 2/3. Example number 10. The square root of 90 over 5. Okay, that fraction, 90 over 5. Well, 90 divided by 5 is 18. So I can rewrite this as the square root of 18. And now I'm going to find the biggest perfect square that goes into 18 evenly. The biggest perfect square that goes into 18 is 9. 9 goes into 18 2 times, so I can rewrite this as 9 times 2 underneath the square root. 9 was the perfect square. The square root of 9 is 3. 3 comes outside, the 2 stays inside. 3 times the square root of 2 is equivalent to the square root of 18, which is equivalent to the square root of the fraction 90 over 5.